Question 7 says, in the circuit shown in figure, well, the circuit is given, 4 statements have been given. Current through 2 ohm resistor is 9 ampere, current through 3 ohm resistor is 6 ampere, voltage drop across 4 ohm resistor is 36 volt, power developed in 5 ohm resistor is 320 watt. Well, this is a section in which one or more than one option may be correct, so we need to evaluate each and every option. Obviously, the question is from the current electricity section. Let's evaluate the options now. We have to find current through 2 ohm resistance. Let's find the equivalent resistance here. So we can see that this 3 ohm and this 6 ohm are in parallel, and 3 ohm and 6 ohm in parallel give you 2 ohm. That 2 ohm in parallel with this 2 ohm will give us 1 ohm. So these 3 are effectively giving you 1 ohm, and so total the effective resistance R is equal to 1. I just described the calculation of 1, and this 5 and 4 in parallel are 5 into 4, that means 20 divided by 9, and so this effective resistance is 29 by 9 ohm, which means the current I, the total current I, is going to be equal to EMF, which is 58 divided by resistance, or 29 by 9. So that means we have 18 ampere current flowing here, right? Now the question arises as to what is the current in 2 ohm resistance. So we can again find potential difference between, let's say, point A and point B. VA minus VB will be equal to 18 into the effective resistance, which is 1 ohm, and so VA minus VB is equal to 18 into 1, that means 18 volt. So now it's very easy to find current in 2 ohm. It will simply be equal to 18 volt divided by 2 ohm, and that means current in 2 ohm is equal to 18 by 2, or 9 ampere, which means option A is correct. What about current in 3 ohm resistance? Again, the potential difference is 18 volt. 18 divided by 3 is giving us 6 ampere, so option B is also clearly correct. Let's look at option C. Voltage drop across 4 ohm resistor is 36 volt. Well, if this is 18 volt and this is 58 volt, so the potential drop across 4 ohm or 5 ohm will be equal to 58 minus 18, that means 40 volt. So option C is not correct. Let's look at option D. Power developed in 5 ohm resistance is 320 watt. So in 5 ohm, power in 5 ohm will be equal to V square by R. We just found it is 40 volt. So 40 square by 5, and that is equal to 40 into 40 by 5, which is 40 by 5 gives you 8. 8 into 40 is 320 watt. So clearly option D is also correct. For question number 7, options A, B and D are correct. Let's go to the next question now. Question 8 says, a point charge plus Q is placed inside a conducting shell of radius R as shown in figure. The shell has charge plus 2Q. Then there are these 4 statements. A says charge density on inner surface of shell is uniform. B says charge density on outer surface of shell is uniform. C says potential at point A is greater than that at point B, and D says potential at point B is greater than that at point A. Well, obviously the question is based on electrostatics and also electrostatics of conductors. In this particular case, the charge plus Q is not placed at the center. It is placed eccentrically at distance r by 2 from the center. So it means the net charge of minus Q is induced on the inner surface of the shell, but it will not be uniform. Okay, the charge distribution on inner shell will not be uniform, and because the induced charge density will be greater at points closer to Q, and so it's non-uniform. On the outer shell, the charge will become then plus 2Q of its own, and then another Q, because the minus Q has been induced here. So there is 3Q plus 3Q charge on the outer surface, and this will be distributed uniformly. We know from the study of electrostatics of conductors that this will happen. We can also understand it this way, that the charge, this plus Q and minus Q induced on the inner surface, these two charges cancel each other's electric field everywhere in the core of the conductor. So the charge plus 3Q on the outer shell will be distributed uniformly. Now with that understanding, let's look at the options again. Option A says charge density on inner surface of shell is uniform. We just saw it is not, so A is incorrect. B says charge density on outer surface of shell is uniform. It's correct, we just described it. Potential at point A is greater than that at point B. Now if the charge here is distributed uniformly, so the electric field outside the shell is directed radially, and by symmetry the potential at point A and point B will be equal, which means statement C is incorrect, and so is statement D. So for question 8, only statement B is correct. Let's now move to the next question. Question 9 says a sound source producing sound of frequency 200 Hz is moving towards an observer with velocity 20 meter per second. The observer is moving away from source at velocity 10 meter per second. If speed of sound is 340 meter per second, then option A says apparent wavelength of sound observed by observer is 1.7 meter. Option B says apparent wavelength of sound observed by observer is 1.6 meter. C says apparent frequency is 216 Hz, and option D says apparent speed of sound is 330 meter per second. Well, obviously the question is based on Doppler effect of sound. Let's evaluate the options now. The first is about apparent wavelength of sound. Now we know that the wavelength is changed by motion of the source. If the source had not been moving, then the wavelength would have been, we call it lambda naught. Remember, lambda naught would be the wavelength if the source had not been moving, and this would have been equal to the speed, which is 340 meter per second, divided by frequency 200, and this is 1.7 meter. But here the source is moving, and because of motion of source the wavelength is altered. So if the source is here and here is the observer, in this direction the wavelength will get reduced, whereas to the left of the source wavelength would have increased. So we are concerned right now with wavelength to the right of the source, and that wavelength will be equal to lambda is equal to lambda naught minus distance traveled by the source in one time period, and that is equal to, let's put the expression Vs into T. This is equal to 1.7, which we found earlier, minus speed of source is 20 meter per second, 20, and T will be 1 by 200 second, 1 by frequency. This is clearly equal to 1.6 meter, which means option A is incorrect and option B is correct. What about the apparent frequency to the observer now? We can use the standard formula. The frequency by the observer is equal to F naught, which is 200 Hz, into V, which is 340. Observer is moving away from the source, so we put here minus 10 and in the denominator we have 340 minus 20. This is equal to 200 into 330 divided by 320. Let's divide by 8. If I divide by 8, 8 4s are 32, 8 2s are 16. So this is coming to 25 into 33 divided by 4 hertz. This turns out to be equal to about 206.25 hertz. So option C is incorrect. And what about the apparent speed of sound to the observer? Well, apparent speed of sound to the observer will obviously be equal to 340 minus 10 or 330 meter per second, because the observer is moving away from the source. So option D is correct. Let's now go to the next question. Question 10 says, a hypothetical gas sample has its molecular speed distribution graph as shown in the figure. Quantities are in SI units. Then there is a graph between dN by du versus u, the molecular speed distribution. Option A says total number of molecules is 1000. Option B says total number of molecules is 50. Option C says root mean square speed of molecules is 25 meter per second. And option D says root mean square speed of molecules is root 50 by 3 meter per second. We can see here that if I write the equation of the straight line, we will get dN by du is equal to 10 minus u. If I simply write the equation of this straight line, this is the equation of the straight line. And the total number of molecules which we have to find to evaluate options A and B is simply integral of dN, right? Now from this we have dN is equal to 10 minus u du. That means integral 10 minus u du. We can see that u is going from 0 to 10. And if we perform the integration, we get it as 10u minus u square by 2, where u goes from 0 to 10. Further putting the values, putting the limits, we get it as 100 minus 50 or simply 50. So the number of molecules is 50. Option B is correct and option A is incorrect. Now we have to find the root mean square speed of molecules to evaluate option C and D. And to do that, we first find average value of u square, the mean square speed. And this is equal to integral u square dN divided by total number of molecules. Now question is, what is dN? From this equation we can again write expression for dN, and that dN is equal to 10 minus u du. We can substitute this value here. So this is equal to u square into 10 minus u du. U goes from again 0 to 10, and the value of n we have already found is 50. This value turns out to be equal to 50 by 3 SI units, and so Vrms is equal to square root of mean square speed, and which is equal to under root of 50 by 3 meter per second, which means option D is correct and option C is incorrect. Let's go to the next question now. Question 11 says, consider the circuit shown in the figure. Initially capacitors A and B are charged and C is uncharged. Switch S is then closed. In steady state, Option A says charge on capacitor A is 40 microcoulomb. Option B says charge on capacitor B is 60 microcoulomb. Option C says charge on capacitor C is 30 microcoulomb. And option D says charge flown through the switch S is 120 microcoulomb. So the question is based on capacitors, and also it makes use of Kirchhoff's loop law. It also makes use of Kirchhoff's circuit laws. So let's close the switch and distribute the charge again. After the switch S is closed, we have circuit like this. A key concept here is this, that the charges of this plate, and this plate together will be conserved, right? So some of the charges on these three plates, that is this plate of capacitor A and left plate of capacitor C and the upper plate of capacitor B, before and after closing of switch will be equal. Now suppose here charge is Q1 and here it is Q2 on capacitor C, then sum of these three charges is equal to 180 minus 70, that means 110 microcoulomb. So here the charge is equal to 110 microcoulomb minus Q1 plus Q2 by conserving the charges. Now this is 3 microfarad and this is 6 microfarad and this is 2 microfarad. Okay, we need to now solve for Q1 and Q2. We can use loop law twice. So if I look at this loop, all three capacitors now are in parallel, and so we can write potential difference is Q1 by 6, and this must be equal to Q2 by 3, which itself gives us that Q1 is equal to 2Q2. Further, we also have potential difference is equal to Q1 by 6, which is again equal to 110 minus Q1 plus Q2 divided by 2. So if I put it as 110 minus Q2 can be written as Q1 by 2. So that means it is 3 Q1 by 2 by 2. Let's simplify further. This is 220 minus 3 Q1 by 4. So we have now 2 Q1 equals, because the factor of 2 will go from both sides. So 2 Q1 is equal to 660 minus 9 Q1, or 11 Q1 is 660, so Q1 is 660 by 11, and that means it is equal to 60 microcoulomb, which means charge on capacitor B is 60 microcoulomb. So option B is correct. Let's look at what is the charge on C. Charge on C is Q2, which is Q1 by 2. So that means charge on Q2 is 60 by 2 or 30 microcoulomb. So option C is also correct. And what about charge on capacitor A now? So charge on capacitor A will be 110 minus 90. So that means charge on capacitor A will now be 20 microcoulomb. So option A is incorrect. And how much charge has flown through the switch? So whatever is the magnitude of change on the charge on this capacitor, capacitor B, is the amount of charge that has flown through the switch. Here it was initially 180 microcoulomb and finally it is only 60 microcoulomb. So that means 120 microcoulomb has flown through the switch. So option D is also correct. So for question 11, options B, C and D are correct. Let's now go to the next question.